everyone. We're going to talk about some differences between how atoms and molecules absorb radiation. And I'm going to draw some UV vis spectra on this slide, one for an atom, one for a molecule. And remember, how does ultraviolet visible radiation interact with matter? That's electronic. So I also could have used the word electronic here. But what is an absorbance spectrum? Again, that's a plot of absorbance versus wavelength. And I'm going to kind of stack these two spectra. Up here in the top, I'm going to sketch the absorbance spectrum for gaseous iron atoms that maybe you would have seen in a flame AA. And then down here, I'm going to sketch the absorbance spectrum for an iron 2 phenanthroline complex that should sound familiar to you if you took lab. And that was dissolved in some aqueous solution. So we have a gaseous atom and an aqueous complex. And to remind ourselves that we're doing electronic spectroscopy in the UV visible region, remember the UV goes from 200 to about 400 nanometers, and the visible goes from 400 to about 800 nanometers. What would the absorbance spectrum of a gaseous iron atom look like? Well, I'm just sketching it here, but here's an example. I'll let you ponder that for a moment, and now let me sketch what the absorbance spectrum of this complex would look like. Here it is. Perhaps something like that. Clearly, these spectra are different. What I want you to focus on is the shapes of the signals. We see that for these gaseous atoms, the spectrum contains these sharp lines, while for this molecular form that's dissolved in an aqueous solution, there's kind of a broad band, isn't there? In order to understand why these spectra are different, we're going to have to think about the energy levels in atoms versus molecules. I'll write that down. Think about the energy levels in atoms versus molecules. Let's talk about atoms. Atoms only have electronic energy levels. Atoms have electronic energy levels only. Now, what do I mean by that? I'm going to ask you to think back to introductory chemistry when you learned about the Bohr model, and there was this small, dense nucleus, and these electrons existed in orbitals far away from the nucleus. So you might have called this your first shell, n equals 1. N equals 2 was your second shell. N equals 3 was your third shell, and so on. And if here is an electron, if a photon with enough energy gets absorbed, that electron can get promoted from the first shell to the second shell. If you increase the energy of that photon, your electron may be promoted from the first shell to the third shell. Another way to represent this process is to show the electrons moving up in energy, because these shells further away from the nucleus are higher in energy. So we need to make an energy level diagram. At the lowest energy, there's our first shell. There's our second shell, there's our third shell, And here comes a photon. It has enough energy to promote our electron from the first to the second shell. And maybe that corresponds to this transition here. So I'll label it as lambda 1 to 2 because we're going from the first shell to the second shell. Now, what if you were to increase the energy of that photon even more and promote your electron from the first shell to the third shell? Maybe that transition corresponds to this line here, the movement of an electron from the first to the third shell. So you see sharp lines because each line represents the movement of an electron from one shell to another. Or in other words, each line, and I'm talking about this line here, these lines that you see in the absorbance spectrum, in the absorbance spectrum, each line represents a transition, or more specifically, the movement of an electron from one shell to another, or from one electronic energy level to another electronic energy level. So that's the story for atoms. What about molecules? Well, molecules have electronic energy levels, but because there's more than one atom in a molecule, and because those atoms are connected by bonds that can vibrate, there are vibrational energy levels, and there are rotational energy levels. So let's draw the lowest electronic energy level in a molecule. I'm going to call that E sub naught. That is our ground electronic state. And I'm going to draw just one excited electronic state. I'll call it E1. This is an excited electronic state. So molecules, yes, they still have electronic energy levels, but where would you find these vibrational energy levels? The vibrational energy levels exist within each electronic state. So maybe I'll just draw a few here. These are vibrational energy levels, and we can also have them in the excited state, or I should say electronic excited state. Here are more vibrational energy levels, and I'm not going to spend much time drawing them on my energy level diagram, but within each vibrational energy level, there are also rotational energy levels. And I should have drawn them going all the way across, but I knew I wouldn't be able to make a straight line. So if you have been in organic lab and you have taken an infrared spectrum of your product using the IR, this is what you were doing. You were staying in this ground electronic state, but you were exciting your molecule through these vibrational energy levels again in that lowest electronic state. So this just represents IR that you might have done in organic lab. But does the existence of these vibrational and rotational energy levels possessed by molecules explain why we have a broad band here? I think it may. Imagine if we have a photon and it interacts with our sample and it promotes our molecule from the lowest vibrational energy level in the ground electronic state to the lowest vibrational energy level in the excited electronic state. Perhaps that has an energy that you would find right there. Now increase the energy of that photon a little bit and you'll be able to go from the lowest vibrational energy level in the ground electronic state to an excited vibrational energy level in that excited electronic state. Maybe that has a slightly higher energy and corresponds to this wavelength here. And keep on doing that. Increase the energy level of your photon to keep getting promoted to those excited vibrational energy levels in that excited electronic state. And you can see that there are a lot of different possible transitions that we may have for a molecule. And this doesn't even represent all of them. What if I started in an excited vibrational energy level in the ground electronic state, like I'm showing here? These would be lower energy level transitions that we would see at longer wavelengths. So the reason we see these bands is because of all these additional transitions that are possible because of the existence of vibrational and rotational energy levels. So let me try to write that down. The vibrational and rotational energy levels yield a large number of transitions, right? You see all of them here that are close in energy, and therefore they appear as a band. So I hope that explains why atoms exhibit sharp lines and molecules exhibit these broader bands in their electronic absorbance spectrum. I've got one more thing I need to tell you about this topic. One additional thing I wanted to mention about this topic is, why is hamburger lower in energy than steak? Because it's in the ground state. Thanks for listening.